For this week, week number 9 we call it, and really for the rest of the semester, we're going to be discussing electromagnetic waves. And this is a very big topic. The first chapter is chapter 31 in the textbook by Bauer and Westphal. And we'll see how the laws of electricity and magnetism have wave solutions. And those waves include visible light and radio waves and X-rays, a whole spectrum of electromagnetic radiation, each part of which is important in some way in science or in engineering. And all described by Maxwell's equations of the electric and magnetic fields. So in this week, week number 9, chapter 31, this is part 1 of the screencast, the theory. And here are the topics. First of all, displacement current. We've learned about charged particle currents. Well, there's another kind of current, which we call displacement current. And adding that to the equations we've studied before for electric and magnetic effects, we get the full theory developed by Maxwell, Maxwell's 4 equations. So here are the equations that we'll discuss in this video. The displacement current density, remember J stands for current density, is epsilon naught dE dt. It's going to turn out that that's a source for the magnetic field, because the curl of B is mu naught J plus J displacement. Now the curl of B is mu naught J is something we've seen before. That's Ampere's law. And Maxwell added something to Maxwell's law, the displacement current. It's not a current of charged particles. It's a current associated with the rate of change of the electric field. So that's the first part. Then the wave solutions. We'll have the set of 4 equations, and we'll show that these functions satisfy those equations. And that's a sort of simplest form of wave solution. These are solutions of Maxwell's equations in vacuum. When I say vacuum, I don't mean there's nothing there. I just mean there's no matter there. There's something there. There are the electric and magnetic fields there. But there are no charged particles, there are no charged currents, there's no matter at all. It's just empty space. And these satisfy the equations of Maxwell's field theory. The next topic is energy transport. We've already seen that there's energy associated with the electric field. For example, the energy stored in a capacitor belongs to the electric field. And with the magnetic field, the energy stored in a solenoid belongs to the magnetic field. Well, with these time-dependent fields and traveling waves, that energy can be transported in space. That energy can be carried along by the wave and transported from one place to another. And the equation is the equation for the energy flux. The energy flux is called the Poynting vector, named after the English mathematical physicist Poynting. The Poynting vector is 1 over mu 0 E cross B. That's the energy flux in an electromagnetic wave. Now that's related to the intensity of light, for example, or the intensity of any radio or of any electromagnetic wave. We define intensity as the time average of the Poynting vector. So intensity has the same unit as the Poynting vector, namely the unit of energy flux. It's energy per unit area per unit time, or it's power per unit time. And as we'll see from when we work out the details of the wave solutions, the intensity can also be written as 1 over c mu 0 E squared RMS, where c is the speed of light or of any electromagnetic wave. Mu 0 is the usual magnetic constant. And the root mean square electric field, well, the square of the root mean square is the mean value of E squared. Mean value over one period of oscillation. The Poynting vector is a vector, so energy will be transported in a certain direction, and the Poynting vector is related to that direction. The intensity is not a vector. The intensity is really the magnitude of the energy flux. It has a magnitude but not a direction. And there's a fourth topic, which is in chapter 31, which I don't think I'm talking about in this video, but there'll be some Lon Kappa problems about it. It's radiation pressure. Just like an electromagnetic wave carries energy, an electromagnetic wave also exerts forces. Light exerts a force on anything that it lands on. Light hitting a surface, not a transparent surface, but an opaque surface, exerts pressure. It exerts a force per unit area. And that radiation pressure is related to the intensity. It's the intensity over the speed of light times a factor which depends on how the light interacts with the surface. So for example, the factor is equal to 1 if the surface absorbs light, but it's equal to 2 if the surface reflects light. So these are all found in chapter 31. They're in sections 1, 2, 4, 5. So in this screencast, I'll describe some of the theory and some of the equations you'll need. And if you want more information about it, read chapter 31. Okay, displacement current. Let's recall some of the field equations that we've studied earlier in the semester. We've mainly been concerned with fields that do not depend on time, but we introduced the idea of time dependence back in week 7 when we considered electromagnetic induction. And recall from that week Faraday's law. The EMF around a closed loop is minus the rate of change of the magnetic flux through the loop. Rate of change meaning rate of change with respect to time. So you see, that's where we introduced time dependence into the study of electric and magnetic fields. Now this is one form of Faraday's law, but Maxwell wrote it a different way, an equivalent way, in terms of the fields. The EMF around a closed loop is the line integral of the electric field around the loop. So it's E dot ds, where ds is a small arc length on the loop, and you integrate all the way around the loop. And Faraday's law says that that's equal to minus the time derivative of the flux of the magnetic field through any surface bounded by the loop. So we introduced the idea of a loop, a curve in space. It's not necessarily anything physical. It could just be an ideal curve in space. And then, put it in a different color, a surface. A surface whose boundary is the loop. So the loop is a curve. And S is a surface bounded by the curve. So in other words, it's an open surface and the boundary is the curve C. All right, the circulation of E around the curve is equal to the negative of the rate of change, or the rate of decrease of the flux through the surface. Now that equation can also be written as a differential equation. Completely equivalent is that the curl of E is the negative time derivative of B. So you see, this is a case where B would depend on time. The magnetic field has a time dependence. All right, this integral relation holds for every curve in space and for every surface bounded by that curve. This differential equation, really a partial differential equation, holds at every point in space and at every time. So these are very general equations. All right, well that was chapter 7, electromagnetic induction. Now recall another topic, Ampere's law. Ampere's law says that the circulation of B around a curve is equal to mu naught times the current going through the curve. In other words, going through the surface bounded by the curve. And again, Maxwell wrote this in terms of the fields. He wrote the integral, the line integral of B dot ds around the curve C is mu naught times the amount of current going through the curve, through the surface. Remember, current, we use the symbol I. But we could write that as the integral J dot dA, where J is current per unit area. So J dot dA is the amount of current going through that little area. And then we integrate over the whole surface. So this is Ampere's law. Again, for a closed curve in space and a surface bounded by that curve. Now again, we can rewrite this differential equation, which has to hold for every loop and for every surface, in a form of a differential equation, partial differential equation. The curl of B is mu naught J. You see how the circulation of E gives us information about the curl of E. And the circulation of B gives us information about the curl of B. And the flux of, well, minus dB dt, minus the flux of the changing magnetic field, gives us information about the partial derivative of B with respect to time. Well, in the same way, the flux of the current going through the area gives us, in the partial differential equation, the current per unit area. And these, in the same way, are very general. This has to hold for every curve in space, and this has to hold for every point in space and time. All right. We're going to find that this equation is not always true. It's only true if the electric field is not changing in time. So this equation is true sometimes. It's true for electrostatics, but it's not true all the time, and that's what we're coming to. Okay, before I write down the equations for displacement current, let me go over a little bit of the history of this development. James Clerk Maxwell was a professor in Scotland and later in England. He lived 1831 to 1879. In the later part of his life, he was professor of physics at the University of Cambridge. That's the old University of Newton. He developed the field theory of electricity and magnetism, working very much alone. He had a lot of colleagues and friends, but he worked on this pretty much alone and developed the whole field theory by himself. And no one else was working along the same lines at that time. So his successes are remembered, sort of comparable to those of Isaac Newton. Now, the field theory describes not only electricity and magnetism, but also electromagnetism and ultimately optics, the theory of light. And physics is a subject that has applications in technology and engineering, all of electrical engineering, and a lot of optics and other kinds of technologies involving waves come out of Maxwell's theory. Here's a little story I found on the internet. Einstein visited the University of Cambridge in 1922. So what was that? 40 years after Maxwell had died. And he was told by his host that he had done great things. Namely, Einstein had done great things by 1922. And his host said he had done great things because he stood on Newton's shoulders. But Einstein replied, "No, I don't. I stand on the shoulders of Maxwell." Now, going back to Ampere's law, the curl of B is mu naught J. That is to say, electric currents, motion of charged particles, create magnetic fields. And this is the field equation which holds for every point in space and time, relating the electric current density at that point to the magnetic field at that point. By sheer mathematical analysis, not experiments, by purely mathematical analysis, Maxwell proved that this equation must be incomplete because it would not agree with the other field equations for electricity and magnetism. Maxwell was a talented mathematician, and he could write the equations and recognize that they didn't agree with each other. So he said, well, all right, in order to construct a complete theory, the correct equation must be, or maybe I should say could be, curl of B is mu naught J plus mu naught epsilon naught dE dt. So in other words, he added something in addition to the electric current, epsilon naught dE dt. And this quantity, epsilon naught dE dt, because it appears in the equation in the same form as J, the particle current density, he named it the displacement current. It's a kind of current density. J sub displacement is epsilon naught dE dt. It exists when the electric field changes in time. In electrostatics, the displacement current is always zero, which is why it had never been seen before in experiments. Because it's rather difficult to do these time-dependent fields in the laboratory. But by purely mathematical analysis, Maxwell said this should be the equation for the magnetic field, for the curl of the magnetic field. And that led to a complete theory of electricity and magnetism. And we use the same theory today. At the time that Maxwell postulated the existence of this effect, you see, it's an effect where a changing electric field creates magnetism. It's a field effect. If the electric field changes in time, there's an associated magnetic field that curls around the change of the electric field. Well, that had never been seen in any laboratory experiments. So at the time that Maxwell published his theory, it was not universally accepted. It was pretty widely accepted in England and Scotland and Great Britain because Maxwell was one of theirs. But the French and the Germans and the Italians, they didn't really buy it at the time when Maxwell published it. And actually the proof, the ultimate proof that Maxwell's theory was true came from experiments in Germany which created electromagnetic waves. But that was after Maxwell had already died. So Maxwell didn't quite live long enough to see his theory become universally accepted. Now here is the theory that Maxwell published around 1865. So think about what was going on in 1865. In England, it was the time of Queen Victoria. And in the US, it was the time of the Civil War. And while those things were happening in England and Scotland, where Maxwell lived, he was originally Scotch, he was developing this theory, which we still use the same theory today. This theory is the basis for electrical engineering. It's got these four equations. Del dot E is rho over epsilon zero, or in integral form, the integral over a closed surface of the electric field flux through the surface is 1 over epsilon zero times the charge enclosed. So in this equation, the surface is not an open surface, as in the case of Faraday's law or Ampere's law. It's a closed surface, like a sphere or something like that. And that integral relation says the flux of the electric field out of this sphere, it's in 3 dimensions, to sort of picture this in 3 dimensions, the flux going out of this spherical surface is equal to the amount of charge inside. And we call that Gauss's law. And Maxwell would have written it this way. The divergence of E is rho over epsilon 0. So here's an integral relation, but here's a point. Here's a relation that has to hold at every point in space. The divergence of E at a point is equal to the charge density at that point, divided by epsilon 0. The related equation is that del dot B is 0, because there are charged particles that create the electric field, but there are no charged particles that create the magnetic field. The magnetic field is created by currents, not by particles. Well, the particles make up a current, but there's no particle for magnetism. You know, the electron, the proton, the atomic nucleus, the quarks, they're point-like sources for the electric field, but there are no equivalent point-like sources for the magnetic field. Now we can rewrite this differential equation as, again, an integral equation. What goes along with the divergence is the integral over a closed surface. So here's a closed surface, a surface that encloses a volume of space. The integral of B dot dA, the flux of B through that surface, is 0. Because there's no particle that produces a magnetic field diverging away from the particle. The curl of E is minus dB dt. That's the field theoretic or the differential equation for Faraday's law of electromagnetic induction. And writing it in terms of integrals, the circulation of E around a closed curve is equal to the rate of change, or the negative rate of change, of the flux of B through any surface that's bounded by the curve. Bounded by any surface S, bounded by C. So that's Faraday's law, and I talked about that a minute ago. And now, with the displacement current, the curl of B is mu naught, that's a magnetic force constant, J plus epsilon 0 dE dt. So this part is J displacement. So there's a current density associated with particles with charge, and there's also effectively a current density associated with a changing electric field, an electric field that changes in time. And once again, we can write that partial differential equation as an integral equation. It says the circulation of B around a closed curve, any closed curve in space, is mu naught times the charged particle current through the surface, bounded by C, plus the displacement current through that surface. And these currents, I and I sub d, are integrals over the surface of J and J sub d. So I is integral of J. J dot dA over some area or some surface like this, really an open surface. So this can either be current density for particles, charge of particles moving through this surface, or for a changing electric field, the change in the electric field flowing through the surface. So that's Maxwell's field theory. In theoretical physics, one postulates some concepts, some principles, some equations, and then that theory should predict some phenomena that occur in nature. So physics progresses by a matter of postulates, and then laboratory experiments. And the postulates are in the form of equations. So we've seen Maxwell's theory of electric and magnetic fields. It describes how currents create magnetic fields, how charges create electric fields, but it should describe more than that. It described something that was not known before Maxwell: electromagnetic waves. And the fact that his theory had wave solutions was discovered by Maxwell himself. And these are solutions that occur in empty space. What I mean by empty space, or sometimes we could say vacuum, is that there's no matter present. There may be matter somewhere else, but it's not in the space where we're looking at the electric and magnetic fields. So in other words, rho, the charge density, is zero in empty space because charge is in matter and there's no matter present. So the charge density is zero and J is zero. There's no, current, electric current comes from the motion of charged particles, but there are no charged particles in vacuum. So we're looking at Maxwell's equations with rho equals zero and J equals zero. And we're going to see that these equations for the functions of position and time, the electric field vector as a function of x and t, and the magnetic field vector as a function of x and t, these solve or obey the four Maxwell equations with some conditions on the parameters. What are the parameters? Well, you see, E is a wave. It's a traveling wave. The electric field is oscillating in the J direction, the Y direction, sinusoidally. So it has a harmonic time dependence and a sinusoidal X dependence. So we have some direction of propagation of this wave. It's in the X direction. So the wave is moving in some direction. I'll call that X. The electric field is oscillating in the J direction. So the electric field is sometimes positive, sometimes upward, because the sign varies between positive and negative numbers. So it sometimes points in the Y direction, it's J hat, but it sometimes points in the negative J direction. And then a little further along in the wave, it points in the plus Y direction. And a little bit further along, it points in the minus Y direction. And a little bit further along, it points in the plus direction, and then in the minus direction. So you see there's a sinusoidal variation of the electric field, sinusoidal dependence on position. All right, that's the electric field. Now the magnetic field is the same, except it's pointing in the Z direction. So here's the X direction, here's the Y direction. Let's put the Z direction in, I don't know, pink. So at some point, the electric field points in a Y direction. And the magnetic field at the same point points in the Z direction. The Z direction is out this way. So there's the magnetic field at that point. At that point where the electric field points in the Y direction, the magnetic field points in the Z direction. Now how about here? Here the electric field points in the negative Y direction, and so will the magnetic field point in the negative Z direction. So here the magnetic field points in that direction. You have to sort of visualize this in 3 dimensions. And here the electric field points in the y direction. The magnetic field again points in the z direction. And here, where the electric field is pointing in the negative y direction, the magnetic field is again pointing in the negative z direction. So you see, the magnetic field alternates or oscillates between the plus or minus z direction. So you have a wave, you have a combined wave. You have an electric wave, put that in blue. So you have an electric wave which is pointing in the y direction. And put this one in pink. You have a magnetic wave which is pointing in the z direction. The wave is traveling in the x direction. So it's traveling in the x direction. The electric field is alternating in the y direction, plus y minus y, plus y minus y, and so on. And the magnetic field is alternating in the z direction, plus z minus z, plus z minus z, and so on. And this whole thing, at one particular point in time, if I took a photograph of it, a photograph at the same time, I'd have this oscillation, combined oscillation in space. So this would be like a snapshot. But if I consider what happens in time, the whole thing moves in the x direction. So this combination of waves moves along in the x direction. All right, so let's call that, like they do in the textbook, we'll call that the proposed solution. And we'll verify that it obeys the 4 Maxwell equations. All right, let's take the first Maxwell equation. Del dot E equals rho over epsilon 0. But no, rho is 0, because this is an empty space. So del dot E should be 0. So let's calculate the divergence of E. Del dot E. It's dx dx plus dy dy plus dez dz. That's the definition of the divergence differential operator, if you've studied advanced calculus. Now, Ex is 0 because E is in the y direction. So this term is 0. And Ez is 0 because E is in the y direction. So this term is 0. So oops, not that one. This one. So the divergence of E is really just dEy dy. And here's Ey. It's a sine kx minus omega t. Well, that doesn't depend on y. So as far as y is concerned, this is a constant. So dEy dy is 0. So that first Maxwell equation is satisfied. And it doesn't have any condition associated with it. Just the fact that it's propagating in the x direction and alternating in the y direction guarantees that the divergence is 0. Now there's also the divergence of B. Divergence of B is dBx dx plus dBy dy plus dBz dz. Now B only has a z component. So Bx is 0, so that term is 0. By is 0, so that term is 0. It's just dBz dz. But here's Bz, it's sine kx. It doesn't depend on z. So the derivative of Bz with respect to z is 0. So that Maxwell equation is satisfied. And there's no real condition. It's just the fact that the direction of oscillation is perpendicular to the direction of propagation. So these are satisfied because the wave is transverse. It's propagating in the x direction, but the oscillations are in the y and z directions. They're in one direction for the electric field and in a perpendicular direction for the magnetic field. So these electromagnetic waves, whatever they are, they're transverse. Now we come to the time dependence. Faraday's law says curl of E is minus dB dt. Is that true? Well, we've got to calculate the curl of E. Now, if you've had multivariable calculus, you know the definition of the curl is given by a determinant. It's kind of like the definition of the cross product is a determinant of the two vectors. You know, if you have A cross B, you'd have AX, AY, AZ, and BX, BY, BZ would make up the components in the X, Y, and Z directions. Well, for the divergence, we just replace A by the components of the gradient operator, d dx, d dy, d dz. So to calculate this 3 by 3 determinant, so it's I hat, j hat, k hat on the first row. Now, nothing depends on y or z. All the dependence is on x. So we'll have d dx, but we won't have any d dy or d dz. Those will both be 0. And as for E points in the y direction. So Ex is 0 and Ez is 0. So the last line is 0, Ey 0. So now calculate the determinant. I have I hat times this little cofactor, which is 0, minus j hat times this little cofactor, which is 0. Now I have k hat times this cofactor, dy dx minus 0. So it's k hat dy dx. In other words, it's k hat. Now differentiate this with respect to x. I'll have E0 times k cosine kx minus omega t. Because the derivative of the sine is the cosine times k by the chain rule. So here's the curl of E for this proposed solution. K hat E0 k cosine kx minus omega t. And now let's calculate minus dB dt for the proposed solution. It's minus d dt B0 sine kx minus omega t k hat. Well, it'll be in the k hat direction, so I can write the k hat in front. The time derivative of sine kz minus omega t will be cosine kz minus omega t times minus omega by the chain rule. And minus omega times the minus sign will be plus omega. So I'll get B0 omega cosine kx minus omega t. And these have to be equal to satisfy Faraday's law. And the equation is satisfied. It has the same direction, k hat. It has the same x and t dependence, cosine kx minus omega t in both cases. It's just that this coefficient and this coefficient must be the same. So this proposed solution works provided E0k is equal to B0 omega. All right, so we've satisfied the third Maxwell equation, but with a condition on E0k, B0, and omega. I mean, we have these 4 parameters in the proposed solution. E0, B0, k, and omega. Well, it turns out those can't all be different. They have to be related. Those aren't all independent. They have to be related by this equation to satisfy Faraday's law. And finally, we have Maxwell's modification of Ampere's law. The curl of B has to be mu naught J, but J is 0. because there's no current in the space. There are no particles in the space, so there's nothing to make up an electric current. But there is a displacement current. So there's mu naught times the displacement current, epsilon naught dE dt. That's Ampere's law with Maxwell's displacement current in empty space. So again, we have to calculate the curl of B. Well, we calculated the curl of E here. By the same kind of calculation, we'll get the curl of B. It turns out to be E naught k will be replaced by B naught k. Cosine kx minus omega t. We'll still have cosine kx minus omega t. And the direction, instead of k hat, will be minus j hat. So I'll leave that as a little exercise for you, a little calculation in multivariable calculus. What's the curl of B when this is the function? And now we have to compare that to dE dt. Well, remember what E was. E was E0 sine kx minus omega t. So dE dt would be E0, derivative of the sine is the cosine kx minus omega t, times minus omega. So here's the minus omega. And E is in the j hat direction. So dE dt is in the j hat direction. So this quantity must be equal to this quantity. And you see, they are equal. This one goes like kx minus omega t. This one goes like kx minus omega t. This one goes like minus j hat. This one goes like minus j hat. It's just that the constant here, B0k, has to be E0 omega. No, the equation is curl of B is mu naught epsilon naught. So the equation has to be multiplied by, or the dE dt has to be multiplied by dE naught d epsilon naught. Sorry, mu naught epsilon naught. So I have to have B naught k is mu 0 epsilon 0 E naught omega. So that fourth Maxwell equation is obeyed, but there's a condition. The parameters B0, E0, K, and omega have to be related in this way. All right, so Maxwell's equations are satisfied. And so Maxwell concluded, well, assuming my theory is true, there are these electromagnetic waves. And they have certain properties. And in particular, E0k times B must be equal to B0 omega. And B0k must be mu 0 epsilon naught E0 omega. So remember these two equations. Those are conditions on the parameters of the proposed solution so that Maxwell's equations will be satisfied. All right, so now let's look at the properties of the plane wave solution. We call that a plane wave because the electric field oscillates in the plus or minus y direction. The magnetic field oscillates in the plus or minus z direction. The whole wave propagates in the x direction. So the wave fronts are planes parallel to the yz plane. The wave fronts are, let's say, the points where E and B are maximum. That'll be a plane perpendicular to the x direction. And those wave fronts travel along as the whole wave moves to the right. And so we call that a plane wave. Now the electric field and the magnetic field both fields have this x and t dependence, sine kx minus omega t. That describes a wave propagating in the x direction, harmonic in time, sinusoidal in space, propagating in the x direction, and the speed of this wave, call it v, is omega divided by k. So we have these four parameters. E0 is the amplitude of oscillation of the electric field. B0 is the amplitude of oscillation of the magnetic field. K, sometimes called the wave vector. And omega, the angular frequency. The wave is sine kx minus omega t. That corresponds to a wave moving with the speed omega over k. So if we imagine some quantity that oscillates like that, and there's the x direction, and you see sine alternates between plus and minus 1, this wave alternates between plus a and minus a, where a is the amplitude. The crests of the wave occur where the sine is plus 1. So these are the crests of the wave. They occur where the sine is 1, and that occurs at kx minus omega t equals pi over 2. Because the sine of pi over 2 is equal to 1. So maybe that would be this crest, would be kx minus omega t equals pi over 2. Now, the next crest over here is kx minus omega t equals pi over 2 plus 2 pi. And over here, the third crest is at pi over 2 plus 4 pi, and pi over 2 plus 6 pi. So there are actually an infinite number of these crests. They occur at multiples, at pi over 2 plus multiples, integer multiples of 2 pi. Because the sine of theta is periodic with period 2 pi. So the sine of theta plus 2 pi is the same as the sine of theta. Or theta plus 4 pi is the same as sine of theta. Theta plus 6 pi is the same as sine of theta. So let's look at one crest. So let's just look at the crest at pi over 2. Kx minus omega t is pi over 2. Now this whole thing is going to bodily move in the x direction. So x will change as time changes. And if the change in x is delta x and the change of time is delta t, then k delta x minus omega delta t must be 0, so that kx minus omega t is still pi over 2. In other words, if I move x to x prime and t to t prime, and I want kx prime minus omega t prime to be again pi over 2, so I'm talking about the same crest in the wave, then delta x times k plus delta t times minus omega has to be 0. So the phase velocity is delta x over delta t. How far did the crest move during the time delta t? Well, delta x. So the whole wave moved with a velocity delta x over delta t. And if you look at this equation, delta x divided by delta t is omega divided by k. K times delta x is omega times delta t. So the velocity is omega over k. Now I figured this out by considering the motion of a crest on the wave, but I could also use one of the troughs here. here, or here, any one of these minimum points, those would also move with the same velocity. Or I could use one of the nodes of the wave where the value is 0. Here's the value 0. For example, kx minus omega t equals 0 is this point. Here's kx minus omega t equals pi. Here's kx minus omega t equals 2 pi. Well, if I just consider this point where kx minus omega t is 0, and I let it move during a time delta t, k times delta x minus omega times delta t would have to be 0. So again, the velocity of the node of the wave has to be omega over k. And now I have these two equations, which are required by Maxwell's theory, which tell me that omega over k, that's the speed of the wave, has to be, on the one hand, E0 over B0, and on the other hand, solve for omega over k, it's got to be, let's see, bring the k over here, bring this to the denominator, B0 over mu 0 epsilon naught E0. So this is wrong. It's got to be B0 No. I don't think this is wrong after all. By this equation, omega divided by k is equal to E0 over B0. And by this equation, E0 divided by B0 is k divided by mu naught epsilon naught omega. So this is a consequence of the first equation. E naught divided by B naught is omega over k. And this is a property of the second equation. E naught over B naught is k over mu 0 epsilon naught omega. All right, now multiply both sides of the equation by omega divided by k. I'll have here omega over k squared is 1 over mu 0 epsilon 0. So omega over k is 1 over the square root of mu 0 epsilon 0. So that's the speed of the wave. It's given by the magnetic constant mu 0, which is determined by magnetic forces, and the electric constant E0 epsilon 0, which is determined by electric forces. And we know the value of mu 0. It's 12.57 times 10 to the minus 7 in appropriate SI units. And we know the value of epsilon 0. It's 8.85 times 10 to the minus 12 in SI units. And if I multiply those together, take 1 over the square root, I get 2.998 times 10 to the 8th. And this would be in the appropriate unit for velocity. It would be meters per second. Now, Maxwell did this very same calculation. And Maxwell recognized that this number is the speed of light in vacuum, something that had been measured long before Maxwell. So he said, look, I take my theory, I have electromagnetic waves, I calculate the speed of those waves, and just coincidentally, it happens to be equal to the speed of light. I don't think it's a coincidence. So Maxwell concluded that light must be an electromagnetic wave. And that makes Maxwell's field theory the fundamental theory of optics. Optics is the theory of light. And not just visible light. You would have the same speed for any frequency and for any wave number. So these wouldn't have to be optical waves. They could be radio waves, or they could be X-rays. Now, at the time of Maxwell, radio waves were not known. Radio waves were developed later after Maxwell had already died by Heinrich Hertz. And Maxwell didn't know anything about X-rays. X-rays were discovered later than Maxwell. But when it was realized that all these different kinds of radiations are electromagnetic, Maxwell's theory says they all have to have the same speed. So a radio wave moves at the same speed as a light wave, a visible light wave. And an X-ray has to move at the same speed as a visible light wave. So the speed of light and of all electromagnetic waves, and we're talking about waves in vacuum, they're moving in empty space where there are no particles, is 1 over the square root of mu 0 epsilon 0. It has a universal constant, it has a universal value, 2.998 times 10 to the 8 meters per second. And in physics, we call that number, we call that speed c. So everywhere in the rest of the semester, the quantity c will mean 2.998 times 10 to the 8 meters per second. And it's equal to 1 over the square root of mu 0 epsilon 0. All right, so in this way, Maxwell showed that light is electromagnetic. The fact that light is a wave phenomenon was known before Maxwell, but it wasn't known what kind of wave. Maxwell's theory showed this wave is electromagnetic. There's another property of the plane waves. If I look at this equation, B0 divided by epsilon 0 is k over omega. K over omega is 1 over c. So B0 over E0 is 1 over c. Or E0 is c times B0. In any electromagnetic wave, radio wave, microwave, infrared wave, visible light, ultraviolet waves, X-rays, gamma rays, they all have the same speed in vacuum, and they all have the same ratio of magnetic amplitude to electric amplitude, 1 over c. So in other words, you can't have a magnetic field, a magnetic wave, without an electric wave. And you can't have an electric wave without a magnetic wave. If you have an electric wave, you must have a magnetic wave with the amplitude E0 over c. And if you have a magnetic wave, you must have an electric wave with the amplitude c times B0. So in these 4 parameters, E0, B0, K, and omega, only 2 of them are really independent. If you give me E0 and you give me K, I can tell you what B0 has to be. It has to be E0 divided by C. And I can tell you what omega has to be. Omega has to be C times K. Well, we've seen an example of an electromagnetic wave. That's not the most general example. That example had the wave propagating in the x direction, the electric field oscillating in the y direction, and the magnetic field oscillating in the k direction, the z direction. So here are the electric field oscillations, and here are the magnetic field oscillations. I guess really logically I should put that down here. Here's positive z. That's called polarized in the y direction. So this solution that we worked out is a plane wave. It's propagating in the x direction. It's polarized in the y direction. But I could have the propagation direction could be anything. I mean, I could have the wave propagating in a different direction. And the polarization could be anything. long as it's perpendicular to the propagation. It has to be a transverse wave. And I don't have to have just one frequency. I could add waves. Waves obey the superposition principle. So I could add waves with different frequencies. And then I would have a wave which didn't have a single frequency. Or I could add waves traveling in different directions. I could have a wave, this is a plane wave. The wave fronts are planes perpendicular to the direction of propagation, perpendicular to the x direction. That would be appropriate for an antenna, I suppose. But if I had a very small antenna, I could have spherical waves. I could have spherical waves that are propagating away from the antenna. Spherical waves can always be written as superpositions of plane waves. So the plane waves are interesting because you can always make superpositions of plane waves. And the plane waves have the simplest form, where E, B, and K, the wave vector K, is just K times K hat, I hat in this case. Those form an orthogonal triad. Be quiet, Tommy. What you barking at? All right, now let's consider energy transport by the electromagnetic wave. We learned before field energies. For example, the energy per unit volume in an electric field, U sub E, is 1/2 epsilon naught E squared. And for our plane wave, E squared is E max squared times sine squared kx minus omega t. That's the magnetic energy. That's the electric energy. Now we have the magnetic energy, which is 1/2 mu 0 B squared. And B was B max sine kx minus omega t. So 1/2 mu 0 B max squared sine squared kx minus omega t. Now I have certain relations between the various parameters. For example, C is 1 over the square root of mu 0 epsilon 0. And also, B max is equal to E max divided by C. So if I compare this maximum field energy for the electric field to the maximum field energy for the magnetic field, 1/2 2 mu 0 B max squared, I can write that as 1/2 2 mu 0 E max over C squared, E max squared over C squared, and mu 0 C squared is 1 over epsilon 0. So 1 over mu 0 C squared is epsilon 0. So the maximum energy in the magnetic field is equal to the maximum energy in the electric field. In other words, because these have the same phase, I can just say the energy density in the electric field is equal to the energy density in the magnetic field. They both go like sine kx minus omega t, sine squared kx minus omega t, and the coefficients, 1/2 epsilon 0 E max squared, 1/2 mu 0 B max squared, are equal. So that's a characteristic of light waves. They carry energy. They have energy. They have energy content because of the energy of the electric field and the energy of the magnetic field. And the energy content is equal for the electric field and the magnetic field. Now that's energy density. What's the energy flux? We call that J of x and t. And you have to be careful. Don't confuse this J with electric current. Electric current is also denoted by J. So we're kind of using the same letter for two totally different things. But it's sort of conventional to call the Poynting vector J. That's the energy flux. It's the energy per unit area per unit time at the point x and at the time t. And for our plane wave, it's in the x direction. The energy is flowing in the direction of propagation of the wave. So its magnitude is energy per unit area per unit time, and then its direction is I hat, because the electric field carries energy in the direction of its propagating. Now this energy numerator here is the energy density, which is the electric field energy plus the magnetic field energy, times the area times the distance. This is energy per unit volume. Volume is area times distance. So this is the amount of energy in a little portion of the wave. So I've got this wave traveling along in the x direction, carrying energy in the x direction. And I'm looking at how much energy is located, let's put it in a different color, how much energy is located in a little volume of this wave. Well, that volume is the area times the distance. And the distance is the speed times the time. This is the time while I'm watching the energy flow through this little area. So I've got this area A. The amount of flow of energy through A is all the energy in this little volume, where this length is c times the time. So the energy flux, well, UE and UM are equal, so I'll just take 2 times UE. UE is 1/2 epsilon naught E squared, then times area divided by area. So the area divided by the area cancels out. Then times distance divided by time. Distance divided by time is the speed. Speed of what? Well, the speed of the wave. So that's c, and the direction is I hat. So 2 times 1/2 is 1. I have epsilon naught. E is the same as EY. C times E. No. EY is also C times BZ. And so I have here epsilon 0 E times E, which is C times B, times another C, times I hat. That is, in fact, 1 over mu 0 E cross B. Okay. So the Poynting vector, the energy flux, is 1 over mu 0 E cross B. This is energy per unit time per unit area. So the unit is watts per square meter. All right, that's the Poynting vector, and that's the energy flux. Finally, we have the intensity. The intensity of an electromagnetic wave is defined as the time average of the magnitude of the Poynting vector. It's 1 over mu naught E cross B, but B is E naught over C. So it's 1 over mu naught E squared over C. It's 1 over mu naught C times the time average of E squared. So intensity of an electromagnetic wave is 1 over mu naught C times the time average of E squared. Now, because E is harmonic in time, the time average of E squared is the maximum or amplitude squared over 2. You know, E is E max times sine omega t. Well, sine varies between plus or minus 1. Sine squared varies between 0 and 1. So the average of sine squared is a half. So the time average will be E max squared over 2. And we also define root mean square. We define the root mean square of E, so E RMS, is the square root of the average of E squared. E squared is E max squared over 2. So this is E max, that's the amplitude of oscillation of the electric field, over the square root of 2. This is the mean square value, so it's the square of the RMS value, so it's ERMS. Take the square root, that's ERMS, and the mean value of E squared is E max squared over 2. So you take the square root to get E max over the square root of 2. So that's the meaning of root mean square. When you have harmonic oscillations, you have the amplitude, or it's sometimes more logical to express the answer as an average. You can't calculate the average of the electric field. The average of the electric field is 0 because it's alternating between plus y and minus y. So as it alternates between plus and minus y, the average value is 0. But the average of the square is the amplitude squared divided by 2. And the RMS, root mean square, is the amplitude over the square root of 2. Some of the answers in the Lon Kappa homework will ask you to calculate a root mean square value of something. Root mean square power or average power, root mean square electric field, and so on. So you have to know this relationship between the root mean square and the amplitude. It's a factor of the square root of 2. Well, okay, there's one other topic in chapter 31. It's the radiation pressure, but I'm not going to talk about that in the screencast. It's section 5, and the radiation pressure is equal to a numerical factor, just a pure number, times the intensity over the speed of light. And again, there'll be some Lon Kappa problems where you have to calculate radiation pressure. So you can find the, well, this is the equation that you need, but you have to know what the factor is. That's discussed in the book. All right, so this ends part 1 of the video. This is the part which gives the theory, and you're going to need all of this theory. You're going to need to know the meaning of all of these different parameters and so on, and the properties of the electromagnetic wave. So I hope you've been taking notes. Now there'll be a part 2 of the video, which will be some example problems. So if you watch the example problems, they'll make use of all of these equations, and you can apply those when you do the Lon Kappa assignment.